In this work, we develop a generic procedure for training neural network policies to imitate motion capture data in a manner that allows for refinement and reuse of behaviors. The procedure consists of two steps. First, we train the neural network controllers to replicate movements from human motion capture data. Second, we refine and reuse these motion controllers to solve high-level tasks. Many algorithms for imitation learning operate in the favorable setting where demonstration trajectories consist of both states and actions. For motion capture, we require that we can imitate without access to ground truth actions, and when the demonstrations may be structurally or dynamically inconsistent with the imitator body. We validate on a simple reaching task. After training a 2-link arm using reinforcement learning, we provide a 3-link arm with demonstrations consisting only of partial state information from the 2-link arm, and it learns to solve the task by imitation. When reinforcement learning with a simple forward reward is applied out of the box on our custom complex humanoid, we find that resulting walking behavior appears unnatural. We first notice that simply initializing episodes during training to poses sampled from motion capture improves the appearance of the behavior. When moving to the pure imitation setting, we find that attempting to match the statistics of every joint angle inadequately constrains the behaviors. Imitating only features invariant to natural body variability, including vectors from pelvis to end effectors, strikingly improves the behavioral quality. We emphasize the policy is entirely generic without any explicit time or phase inputs. The same approach can be applied to the behavior of getting up from the ground, as well as running and turning. For running and turning, the behaviors were learned from only a few seconds of motion capture data. Moreover, we can take unsegmented, roughly 10-second clips of motion capture data of non-standard styles of walking and learn a policy from scratch that produces meandering behavior and is robust enough to permit limited manipulation via interactive perturbations. Our method allows the imitator to naturally discover transitions between skills. By training a policy which switches between sub-skills, like running and turning when a context signal is modulated, we can keyboard control the character to play games. Once a behavior is learned, it is straightforward to tune in a task-oriented fashion. For example, to climb stairs and descend them without distorting the behavior on flat ground. Finally, we train a higher-level controller that modulates the lower-level context in lieu of user input to solve a corridor navigation task. The approach we have described is a step towards more automatic construction of humanoid behaviors for flexible control.